So first things first, everything you just saw isn't real. Or at least, it's an optical illusion. We can't see the effect with our eyes in person. However, through the lens of a camera, using a few tweaks, it becomes completely different. Now, when we think of optical illusions, we typically think of perspective-based image manipulation. But rather than still pictures like these, it is also possible to find a constantly moving object that generates an optical illusion, such as this one. During the clips you've seen, a tube is attached to the front of an open speaker. The tube begins to pour water at it. You then hook the speaker to a laptop and play a single tone. Now, a tone is, to our ears, a note, basically. It sounds like this. That was a tone of 1000 hertz, which means that 1000 waves just pass by every second. For this experiment, the tone must be played at 24 hertz, which is extremely low sounding. The very last step to making this experiment work is to film it. And to film it at 24 frames per second, or in other words, at 24p, meaning the camera will be taking 24 pictures every single second. The result of this is what you saw at the beginning. But what would happen if you were to play a tone of something other than 24 hertz? What would happen if you were to play a tone of, say, 23 hertz or 25? How would these slight differences in frequency change the effects of the water? Well, that's what we'll find out. After a bit of research, I hypothesized that when I played a tone at 24 hertz, the water would appear as if suspended in the air in the form of a wavy line. I thought if I played a tone of 23 hertz, the water would appear as if it were moving backwards into the tube in that same wavy formation. And if I were to play the tone at 25 hertz, it would do the opposite of the last one and would appear to be moving forward out of the tube in a slow motion, in the same bendy way as the others had. So to begin the experiment, you'll need a 12-inch subwoofer, vinyl tubing, a high place to put the speaker on, we used a chair on top of a table, a water source, tone-generating software, a camera that films at 24p, duct tape, and tolerant neighbors that won't mind loud noises. After acquiring these items, you'll need to set it all up, with the tube attached to the speaker hooked up to a device that can generate a tone, and the camera ready to film. Only then can you begin the experiment. At 24 hertz, the water moved in the exact fashion I had hoped it would. At 23 hertz, it looked like this. And at 25 hertz, this was the result. So the reason why the first one works is because of the synchronization of both playing at 24 hertz and filming at 24p. Since the speaker is vibrating in a specific pattern, it causes the tube to vibrate in the same way, and thus the water to come out in the same way, which results in the water separating and forming droplets. As the water falls, this is where the 24 frames per second comes in. The speaker is sending out 24 sound waves per second, while the camera is taking 24 pictures per second. Since the water is constantly moving downwards, the camera captures the same water shape. As As an example here, this is the tube. When the water droplet comes out of the tube and hits the red dot, it turns yellow. This indicates that the camera has taken a picture. If you were to put yourself in the camera's perspective and black out all that the camera didn't take a picture of, it would look like this. It looks exactly the same. What seems like the same droplet staying in one place is actually many droplets being captured in the same position. This phenomenon can be placed in many different situations. One person puts it in this way. Imagine a clock with only a seconds indicator. If you were to close your eyes and open them precisely once every 60 seconds, you would think the indicator is not moving. And the same goes for this helicopter. It's exactly the same phenomenon used in the water experiment that makes the blades look as if they're not moving, when in reality, they're moving at the same exact speed that the camera is filming at. But this all only explains the 24 Hz one, the one that makes the water seem completely still. What about the others that make the water seem as if it's moving? That's where things get a little more complicated. 23 Hz is lower than 24 Hz, and therefore is slower. So as the droplets fall, they are a tad bit slower than the camera's pictures. And because of its slight desynchronization, each frame seems to show the droplet not quite dropping as far as before, which makes them seem as if they're moving in an upwards formation. And it's the same idea for the 25 Hz one, except the water is dropping faster than the camera is taking pictures, so it's moving in a downwards direction. And so, to end on a philosophical note, although the hows and whys of science are not always answered and understood, it's good to know the basics about the world, such as sound and sight, because sometimes they come together to form awesome stuff.